So today's section is not all that deep. I think in it we basically try to take the notion of dot product and then extend it to abstract vector spaces. So we try to create a dot product for, right, so you've got Euclidean spaces, you've got your abstract vector spaces, you have your dot product over here. Well, what should be analogous thing over here? So we make up something that's basically like the dot product in the abstract case. And this thing that we create is called an inner product. Oops. Inner product. So inner product spaces. Okay, so let's start off with the definition. We say let bracket from v cross v into r be a binary operation. On v. Okay, so by a binary operation, I mean something like addition or multiplication, right? If you have addition, you need two things. You add them together, and you get something else, right? Same thing here. You're going to take two vectors. You're going to do some sort of product with them, and you get a number. Okay, just like the dot product. The dot product, you take two vectors, you dot them together, and you get a number. So that's what this notation means. This thing, it has two holes in it. You fill the two holes with vectors, and out pops a number. Okay, it seems like sort of like a function, but it has two input slots, okay, rather than the normal way. Okay. Let this be a binary operation on V. We say that this thing is an inner product on V if the following three conditions are satisfied. So one, the inner product of x against y equals the inner product of y against x for all x and y in your vector space. Okay. So that is, you've created this product, and it doesn't matter what order you do them in, right? Just like the dot product, right? V dot, u dot v and v dot u are the same thing. Okay. So it's commutative. The product is commutative. Two, alpha x plus beta y inner product against z equals alpha x against z plus beta y against z. Okay, for all x, y, z in V, and alpha and beta in your real numbers. Okay. This is basically that you can you see that this actually has, you could think of this as having two parts, right? X plus y against z equals xz plus yz, right? So that you can write this in a different way as having two parts. This and alpha x y equals alpha x y. Okay, those two together are the same thing as this. Okay, if you want to, I actually find this easier to understand. What this says is that you can add these guys and then multiply them, or you can multiply them and then add them. Right here you can multiply by a scalar and then do it, or then multiply them and then take the scalar after. Yes, yeah.
Does it mean it's a linear transformation?
It means, this is what we call linear. So it's, this is linear in the first variable. It's linear in the first variable. But since the thing is commutative, so just as a remark, since the thing is commutative, it's also linear in the second variable, right? Because if this stuff were in the second variable, you could move it, you could just flip it, and then use the linearity in the first variable. So, because of the commutativity, and because of 1, it's linear in the second. It's also linear in the second. Yeah, Laura.
Are you confused with the second part of the 2 prime complex?
So this is a scalar.
Okay.
This is a scalar. Right? Just like if you have the dot product and you have like 5 vectors, 5u dot v is the same thing as 5u dot v. That's all we're saying here, right? That you can multiply by the scalar and then do the dot product, or you can do the dot product and then multiply by the scalar.
Is it a binary operation? Does that mean the dot product, or is that something else?
No, it just means something like the dot. It just means something that something that takes 2 elements of here and then gives you some number back. Okay, something that takes in 2 vectors and then gives you a number back. So the dot product is one example, right? The dot product, right? You put in 2 vectors and it gives you a number.
Okay. Wait, so here are we doing the dot product, or is it supposed to be something analogous?
This is something analogous. So we're basically sort of pulling off the important properties of the dot product and saying anything that has those properties, we're going to call an inner product. Okay. Just like when we talked about abstract vector spaces, we had the Euclidean vector spaces, and then we said, okay, anything that has such and such properties, and there were like all these vector space axioms, is called a vector space. Okay, it's the same thing, right?
Okay.
We have the dot product. We think, well, what does the dot product do? Well, the dot product has this property and this property, right? And it also has one more property. The third property is that if you take the dot product of a vector against itself, what kind of a number do you get? Can you get a negative number? No, right? So the number is always greater than or equal to 0. Okay. Further, the number equals 0 if and only if the vector is the 0 vector. Okay, right. Okay, so if all these 3 things happen, then we say that this thing is an inner product, right? Remark. In that case, we call the vector space with the inner product and inner product space. Which I'm always going to abbreviate IPS. Okay, so the sort of simple example is if V is Rn and our inner product is the dot product, right? Then Rn with this dot product is an inner product space. Right? Because it satisfies all those 3 properties. Let me just ask you one question. Suppose you know that the is it true that if b dot b equals 0, then b is the 0 vector? Is that true? You have two vectors, you take the dot product, two Euclidean space vectors, take the dot product, you get 0. Does that tell you that v is a 0 vector? Yes, yes, because b dot b is going to be summation, it's going to be b1, b1 squared plus b2 squared, etc., right? b1 squared plus b2 squared plus bn squared, right? Okay. And if that equals 0, then what do you know? Then they all have to be equal to 0, right? Because these are positive or non-negative numbers, right? If v dot v equals 0, then all vi must be equal to 0, right? Because if you have somebody who's non-zero, well, you're not going to put 0. Okay. So, so this is something that you have to check. Right? If somebody said, is this thing an inner product space? Well, you have to check all three properties. So we checked part of the third property here. This is actually the hard part of the third property. Yeah, Mariah.
Wait, so like the inner product space, like you have like a curly bracket V and then like something that's like dot product, that is the inner product space?
Yeah, so these two things together, the vector space and the inner product, together we call the inner product space.
So would it just be made up of like two vectors? Like what is inside the triangle bracket?
So let me say it this way. Any vector space with an inner product is called an inner product space.
Oh, so if it could have, like if it has an inner product?
No, you have to specify the inner product.
Okay.
Because you could have one vector space with multiple inner products, actually.
Okay. So it's like a particular inner product space.
Yeah.
And there are many potentially.
Yeah. So all this is saying is that if you have a vector space and you have an inner product, then we call the pair of the space and the inner product space 110.
Could you give an example of another inner product?
Just about.
Okay.
Just about. Yeah. Fun.
Yeah, I'm still unsure what an inner product is.
What an inner product is?
Yeah.
An inner product is a way of multiplying things. Okay. So like in Euclidean space, we have the dot product. Right? The dot product is a way of multiplying two Euclidean vectors. Okay. Right? And that product has certain properties. Okay. If that product satisfies these three properties, then we call it an inner product. Okay. So the dot product actually does satisfy these properties because the inner product is actually based on the idea of the dot product. So, by construction, the dot product is an inner product. Does that help? So it's just a way of multiplying things. So you have your Euclidean space, you have some way of multiplying things, and this way of multiplying things satisfies those three properties. That's an inner product. Okay, we're going to give lots and lots of examples of inner products. Ethan.
So, but you said it can be a binary operation. So that means this is just for a multiplication method, right?
It means that it's something that takes in two vectors. Binary because it takes in these two entries.
Oh.
Okay, let's give a couple more examples. We'll give a few more examples of inner products. Okay, so example 1 prime. So that was actually example 1 up there. Example 1 prime is, again, let's take Euclidean space, But now we're going to make a sort of funny dot product. Okay, we create pick a vector W in Rn where all the entries are bigger than 0. Okay. All the entries are bigger than 0. Okay. So like if we're in R2, 1/2 would be, anything with any vector with where all the entries are bigger than 0. Okay. We create a new product, UV, defined as summation UI VI WI. Okay. UI VI WI. Okay. So you see the difference is that we throw in, we multiply the products by these numbers. Okay. So maybe you could say, so your normal dot product ABC dot DEF is AD plus BE plus CF, right? But now we create some sort of weighted dot product. So you can choose your weight however you want. So maybe I'm going to choose my weight to be 1 to 1,000. Okay? And what that would say is that whenever you multiply ABC dot DEF, I create this new dot product. It says take AD plus 2BE plus 1,000 CF. Okay, so it weights it weights the third variable for some reason. For some reason, you really care about that third variable, and you don't care too much about the other two variables. Okay. Okay, so you create this new weighted product, and we claim that this is also an inner product. It is not the dot product, right? It's not the dot product that we had before, but it's a different inner product on Euclidean space. Okay, so to show that it is an inner product, we have to prove those the three facts, right? So is it true that so is this an inner product? Right? Is it true that UV equals VW? VU, excuse me? Is UV equals VU? Sure, right? Because you just change the order, right? Just change the order, it's the same thing, right? Yes, right? Is it true that U plus V against W is the same thing as U against W? I shouldn't use W because I use W for something else. X plus Y Z equals XZ plus YZ. Is it true that alpha XY equals alpha XY? Yeah, in fact, they're all true. So is it true that, for example, the vector against itself is bigger than or equal to 0? Well, we're going to get summation. Well, what do you think about it? Is it true? Sure, right? Because a vector against itself will be summation vi squared wi. Right? This would be summation vi squared wi, but the wi are all positive, right? So this is still going to be positive, right? Or non-negative, right? Is it true that if VV equals 0, then V must be the 0 vector? Sure, same reasoning, right? If this equals 0, that means that all the VI must have been 0, right? Okay. Same argument. Yes, same argument. Okay. So yeah, so this is an inner product, and you see, Montana, that now we can make infinitely many different inner products on Euclidean space by just picking different weights for it. These guys are called weights. Okay.
Is it different from like the scalar, or am I just thinking like the scalars above, like alpha, beta? There are other vectors.
Say it again.
Is it different from like the alpha, beta scalars above? Because there are like other vectors, the WI.
Alpha and beta are numbers,
Yeah.
right?
Okay.
So this is something where so whenever you create a new way of multiplying, basically, right? And you say, whenever I multiply anything, I'm going to throw in these extra numbers. Okay, and it changes. These numbers are going to change. These numbers are different depending on what entry we're multiplying.
But those are vectors, right?
These things. So you see here, right? Like we're going to get the different components are going to get multiplied by different numbers. These alpha and beta up here are multiplied the whole vector through, right? So it's not at all the same thing. Is this sort of making sense? Anybody have questions? Any other questions?
And so how do you see that the second one is true?
The second one is true?
Yeah.
Okay, let's just do one of them, right? Okay, let's do the top one here. X plus y against z. Well, that would be summation xi plus yi zi wi, right? From I equals 1 to n. So that's the left side, right? What's the right side? We're saying, is that the same thing as x against z? So xi zi wi plus summation yi zi wi. Right? And you say, sure, yeah, I mean, this is, you just distribute this, right? This is xi zi wi plus xi zi, I'm sorry, yi zi wi. Right? And those are the same thing. Okay, so it's just a calculation. Okay, more examples. And kind of a dumb one. Example 2, I guess. So example 2, let A and B be matrices. Let A and B be matrices. Define an inner product on matrices in the dumb way of just taking the sum of all the products of the corresponding entries. Right? It's not interesting. Right? You're basically just pretending that these are long vectors. That's it. That's a dot product, not surprisingly. Okay, right. More interesting, let V be the continuous functions on AB. Right? Continuous continuous functions on the interval AB.
Is this a different example?
Yeah, example 3, sorry. Yeah, number 2 was too boring, and so we finished it already. Number 3, more interesting. The vector space of continuous functions. So your vectors are functions, like the sine function, or some polynomial, or whatever. Okay? So you've got continuous functions. Define a dot product by taking the integral of the product. So you multiply those two vectors together, multiply the two functions together, and take their integral, take the definite integral over AB. Okay. It turns out that this turns out to be an inner product. Or more generally, we can create if we have a function suppose we have some function that's positive everywhere, we can make a weighted inner product for the continuous functions. We can make a weighted inner product for the continuous functions.
Is that W parentheses X or W?
W parentheses, sorry. So, I mean, we'd actually have to prove that, right? We'd have to show that these things are inner products, but I'm gonna skip this one. I'll let you think about it if you want. The hardest part is showing that if the inner product of f against f is 0, then f must be the 0 function. Okay, that's actually not so simple. So let's skip that actually. So let's do the last example of an inner product. So let V be piece of n. Remember the polynomials of degree less than n. Polynomials of degree less than n. Okay. So we're going to do something funny. We create an inner product. We can create an inner product by so as follows. Okay, choose n distinct points in Rn in R. Choose n distinct points in R. x1, x2, x3, through xn. Okay. Choose n distinct points, and we're gonna make an inner product for the polynomials like this. We define the inner product of polynomial p we define the inner product as the sum of, oops, the products of the values of the polynomials at those endpoints. Yeah.
I'm not really sure what you mean by endpoints.
Yeah. So let's make it concrete. So for example, so for example, like suppose we're in P3. Okay. P3 polynomials of degree less than 3. Okay. We choose 3 points. Here they are: x1, x2, and x3. Okay. They can be any, whatever 3 points you feel like. Okay? 0, 1, and 5, say. Any 3 points. And we say we're going to make an inner product like as follows. So notice that all the polynomials of degree, these guys are either lines or parabola, right? So I'm going to just draw them as parabola. Okay, so you've got one guy and you've got another guy. Okay, and we say the inner product of these guys, the product of these guys, we're going to define the product to be, we take the values at those points, right? P of x1, Q of x1, and multiply them. And then P of x2, Q of x2, multiply them. P of x3 and Q of x3, and we multiply them. And we add those 3 products together, and that's what we're going to take as our product of the polynomials. That will be our inner product of the polynomials. Okay. Okay. It seems kind of weird, right? Like, is that how we're going to create an inner product? But claim this is an inner product. This thing actually is an inner product. Okay.
And then the inner product space is like that thing and Pn.
Yeah. So Pn with this inner product is called an inner product space.
Is the space like actually like a space? Like for example, like R2 or something?
So basically you consider this thing to be the space
Yeah.
and that thing to be the inner product on the space.
Oh, okay, inner product on the space. So
Yeah,
it's
and
not
then-
like an inner product space.
Well, the two together, this, I mean, as long as this thing has an inner product, we call it an inner product space.
Oh.
Okay. But you have to, yeah. Yeah.
Is it a subspace?
Is it a subspace? I mean, this is a subspace of, it is, I mean, this is Pn. Oh, so not exactly, right? I mean, so this V is certainly a subspace of, Pn plus 1 or something like that. But you don't call, like...
I mean, the inner product space is a subspace.
Right, no, not exactly, right? Because the inner product space, I mean, this is sort of just wording, right? You don't, when you say inner product space, you mean you mean this vector space plus the product itself, right? So, okay, and you don't get too hung up on the words. An inner product space is just a vector space that has an inner product and a vector space plus an inner product. Okay, so let's look at this thing. So this is the okay. So one simple one. Is it okay to change the order? Is P against Q the same thing as Q against P? Sure, right? Because you would just change the order here. Doesn't matter what order you multiply numbers, right? So that's fine. Right? The linearity also turns out to be fine. The one that's tricky is the following. Show that if P against P equals 0, then P must be the zero vector, in other words, the zero polynomial. Suppose you know that the inner product of P against P is 0. Then P must be the zero polynomial. 110.
Since you're taking n points, that means that you can't have n intersections with the x-axis. Like, you can only have up to n minus 1 intersections with the x-axis. So even, so anytime that there's more than that, they both have to just be the x-axis.
Exactly. Right, so you say, well, look, if P against P is 0, that would mean that summation P xi squared equals 0. Right, in other words, px1 squared plus px2 squared plus pxn squared equals 0. Right, if P against P equals 0, then this would be equal to 0. But that means that each of these things is 0, right? So that means that P of xi equals 0 for all I, right? But P was of degree less than n. P was a polynomial of degree less than n, and we're saying that it has n roots, right? There are n places where this polynomial of degree less than n is equal to 0. Well, that can only happen if it's a zero polynomial, right? You can't have a polynomial of degree 2 which is 0 at 3 points, right? You can't have a parabola that intersects the x-axis at 3 points unless it's the zero parabola, right? Right? You can't have a line that intersects this at 2 points except if it's the zero line, right? Any polynomial of degree less than n that intersects the x-axis that has n roots has to be constantly 0. So yeah, but that would imply that P is constantly equal to 0. Okay, so once you have an inner product, then you can introduce all sorts of things from Euclidean space. So the first thing we can talk about is orthogonality, right? Things being perpendicular. Once you have an inner product, you can say things that are perpendicular if their inner product is 0, right? So we say let U and V be in some inner product space. So suppose you have two vectors in an inner product space. If their inner product is 0, and we say that U and V are orthogonal. Oops. Okay. So we can talk about things being orthogonal. And of course, once we can talk about vectors being orthogonal, we can talk about subspaces being orthogonal, or orthogonal complements, et cetera, in the abstract vector space setting. Right? Okay. So for example, in the continuous functions on -1, 1, f of x equals 1 and g of x equals x are orthogonal because the integral between -1 and 1 of 1 times x is 0. Right. The inner product of 1 against x, you take the function against the other function, integrate between -1 and 1, you get 0. And so these functions are perpendicular to each other. Okay. So we can talk about a kind of geometry, right? Functions being perpendicular to each other. Okay. Second definition. This is basically like the idea of magnitude. We define the norm of V as the square root of the inner product of the vector against itself, just like we do in Rn. Right, in Rn, you can take a vector dot product against itself, take the square root, you get the magnitude, right? So that's how we're going to define this thing, the magnitude or the norm in the general inner product space. Okay. Another definition. If you have U and V in the inner product space, we define the vector projection of U on V as the inner product of U against V over the inner product of V against V times V. So we just use the Euclidean definition, and then we, just switch it over to the inner product definition. Switch it over to the abstract inner product. We're just using exactly the same definition from Euclidean space. Right, this is equal to, you recall that this is equal to this. Right, if you like to think of it that way. I do. So this is the vector projection of one vector on another. Okay. Just like in the Euclidean case, we're going to call this number the scalar projection. So that number is the scalar projection of U on V. Okay. So once you have an inner product, right, you can talk about things being perpendicular to each other. You can talk about magnitude. You can talk about projection, right? So even in the space of functions, right, you can project one function onto another function. You can talk about the size of a function, right? This sort of thing. Okay. Other things that you can do that you have are the Pythagorean theorem. Right, so if U and V are in the inner product space V, if U and V are perpendicular, to each other, then the magnitude of U plus V squared is going to be the magnitude of U squared plus the magnitude of V squared. Okay, but the proof of this, we actually did the proof of this last time. It's the same. Yeah, it's the same proof that we did last time. Say, well, look, the magnitude squared is just the inner product of the vector against itself. Right? But by linearity, that's u against u plus v plus v against u plus v. By linearity in the first variable. Right? I mean, you just think of it as distributive property. Okay. Using linearity in the second variable, you get u plus uv plus vu plus vv. Right? But as we saw last time, these guys are 0, and so you end up with the magnitude of u squared plus the magnitude of v squared. Okay. So in an abstract inner product space, you have a Pythagorean theorem, right? You have a Pythagorean theorem, even though there are no triangles, right? There are no triangles. And you can talk about functions being perpendicular to each other, right? So, right, for example, in the continuous functions on negative pi to pi, cosine and sine are perpendicular. Cosine and sine are perpendicular, and so you can use the Pythagorean theorem on them, right? The norm of the sum squared equals the norm of cosine plus the norm of sine squared. Even though there's no triangle here, then you can see. Okay, we're going to stop here for today. Let me hand back the exams. So the exams, I hear a groan. So the exams range quite considerably. Like, this is not the exams. The exams ranged quite a lot. There were people who did very well, and there were people who did very not that well, actually. So those of you who did not do well, come to office hours. So I'm going to look. I'm going to look this way. Those of you who did not do well, come to office hours, and and I'll try to help you, right? Because there's no reason anybody should be, everything in mathematics can be broken down into something more simple. I'm going to look at you, Sally. You were not one that did poorly, so I'm going to look at you. Okay. Everything in mathematics can be broken down into something simpler, right? It's not like we make one statement that is completely impenetrable. That impenetrable statement is broken down into smaller impenetrable statements, right? Can be broken down into even smaller statements, which can be broken down into simple statements, right? So eventually, you break it down to something where you understand it, right? There's nothing impenetrable about mathematics, right? So if you are lost, then it's because I haven't broken it down far enough. Okay, so come to office hours, and if there's more time in office hours, I can break it down farther. Okay, so so don't be discouraged. I told this to my other class, actually not the other linear algebra class, but another class that had some depressing grades. But that, so like in my first theoretical math class in college, which was the first math class I took in college, I didn't understand anything, and so I went to the professor. And I said, Professor, And this is Professor Wiles of Fermat's last theorem fame, if you know this story. I said, Professor Wiles, I don't understand anything. I just don't get this at all. And he said, don't be discouraged. He said, don't be discouraged. When I first took a theoretical math class, when I first picked up a theoretical textbook, I could not understand it at all. And just keep on going. And that's all he said. He actually didn't even say keep on going. He said that's it. That was the end of the statement. Don't be discouraged, right? So don't be discouraged. Just keep on going, and you'll get it. I think everybody should be able to get it. So okay. So let me. I'm happy to do that.